Good morning. In the last lecture, we saw the Hamming codes, which are single error correcting codes. We also saw a simple decoding algorithm for all single error correcting codes. In today's short lecture, I'll introduce the notion of a perfect code, and we'll see that all the Hamming codes are perfect codes. There are two other interesting perfect codes, the ternary Golay code and the binary Golay code C23. We'll study C23 in Chapter 4. Let C be an NM block code of distance d over an alphabet A of size q, with error correcting capability d-1/2. Then the code C is said to be perfect if each vector of length n over A is in the sphere of radius E centered at some code word. In terms of this Venn diagram, which contains all the vectors of length n over A, recall that we can look at the spheres of radius E about the M code words. We proved that since the code is an E error correcting code, no two of these spheres can overlap. However, there could be some vectors such as these, which are not in any of the spheres. The code is perfect if there are no such vectors which do not belong to any of the M spheres of radius E about code words. Equivalently, the code is said to be perfect if it meets the sphere packing bound with equality. The right-hand side of this inequality counts the number of vectors of length n over the alphabet, while on the left-hand side you have the number of spheres m, and the summation is the number of vectors in a sphere of radius E about a code word. And so the left-hand side counts the total number of vectors and all the M spheres of radius E centered at the code words. Equality means that there are no vectors in the Venn diagram that do not belong to some sphere of radius E about a code word. The reason these codes are called perfect is that for a fixed alphabet size, length, and distance, a perfect code has maximum possible number of code words. We can't possibly pack any more of these spheres of radius E into the picture because there are no leftover vectors. In other words, for a fixed alphabet size, code length, and distance, the perfect code has maximum possible rate, which is log base q of the number of code words divided by the code length n. Let's look at some examples of perfect codes. The trivial code, which consists of all vectors of length n over the alphabet A, is a perfect code with distance 1. Not a very exciting perfect code. It's useless because the distance is 1, and so its error correcting capability is 0. Here's a less trivial example of a perfect code. Let n be odd. Then the binary replication code of length n, which is comprised of two code words, is a perfect code with distance n. Let's verify that this code is perfect. Its error correcting capability is n-1/2, which is an integer since n is odd. Let's evaluate the left-hand side of the sphere packing bound. The number of code words m is 2. Q is 2, so this term is 1. And hence, since E is n-1/2, the summation is the sum of the first E plus 1 binomial coefficients. Now we know that the binomial coefficient n choose k equals n choose n minus k. And so, since I have two copies of each of these binomial coefficients, I can replace one of the n choose e's with n choose e plus 1, one of the n choose e minus 1s with n choose e plus 2, and one of the n choose zeros with n choose n. And so this expression equals the sum of all n plus 1 binomial coefficients. By the binomial theorem, this equals 1 plus 1 to the power n, which is 2 to the n. This is the right-hand side of the sphere packing bound. And so we've established that the binary replication code of odd length is a perfect code. As an exercise, you can prove that every perfect code has odd distance. Another exercise is to verify that IMLD is identical to CMLD for perfect codes. The Hamming codes of order R over GFQ are a non-trivial, infinite family of perfect codes. Let's justify this. The Hamming codes have length q to the r minus 1 over q minus 1, dimension n minus r, distance 3, and error correcting capability 1. Let's evaluate the left-hand side of the sphere packing bound. The number of code words m is q to the k. E is 1, so the summation has two terms, n choose 0 q minus 1 to the 0, and n choose 1 times q minus 1. The two terms simplify to 1 plus n times q minus 1. I'll replace n by q to the r minus 1 over q minus 1, and then cancel the q minus 1 terms to get q to the n, the right-hand side of the sphere packing bound. So the sphere packing bound is met with equality, and this shows that all Hamming codes of order R over GFQ are in fact perfect. Unfortunately, there aren't many more perfect codes. In 1973, this Finnish person, whose name I can't pronounce, proved that the only perfect codes that exist are the trivial codes consisting of all n tuples over GFQ, the binary replication codes of odd lengths, the Hamming codes, and all block codes with the same NMD parameters as the Hamming codes. There's a special linear code over Z2 of length 23, dimension 12, and distance 7, called the binary Golay code C23, and all codes that are equivalent to it. We'll study C23 in video lecture 4a, and there's a special ternary Golay code of length 11, dimension 6, and distance 5 over the integers modulo 3, and all codes that are equivalent to it. The generator matrix for this ternary Golay code is the 6 by 11 matrix in standard form over the integers modulo 3.
In V3f, we'll see the notions of cosets of a code and syndromes of vectors. This will lead to a decoding algorithm called syndrome decoding that works for all linear codes. We'll see you then.